This week we're going to look at encoding and data compression. We're going to look at 4 different ways we could compress data or encode. Now, encoding and data compression are not the same thing, but we will see that they are related. So encoding means we want to send a message somewhere to somewhere else so that if it's intercepted, it can't be read, but so that if it is sent to the other place, to the other person, for example, then that person could decode it and figure out what you're trying to say, provided that that person knows what rule you used to do the encoding. For data compression, we're going to look at a couple ways we could, compress data. So take a sequence of information or a set of information that takes a certain amount of space and see how we could rewrite it or rearrange it or rethink of it. That's the better. Rethink of it so that it's taking up less space. And we're going to look at 4 different topics this week. First, we're going to use a Venn diagram to encode a 4-digit binary string. So first we'll say Venn diagram method. So the Venn diagram method. Now this method is going to be used only to encode and decode a 4-digit binary string. Binary string meaning 0s and 1s. Binary strings show up a lot. Last week we talked about identification numbers. One we didn't talk about was the barcode that shows up on products. Now barcode, do I have one near me? Yes, barcode. So right here, it's a bunch of numbers at the top, in this case of this DVD, or not a bunch of numbers, a bunch of bars at the top of the DVD, and it's scanned by a ray of light, and the white spaces between the black bars reflects back light. And how much light is reflected, the computer that's doing the scanning is going to turn those widths of light into sequences of 0s and 1s. And that's how the machine actually interprets something like that. Now how it actually does that, I'm not too concerned with your knowing, but it is cool to know that that is what it does. In section 16.2, it talks about that in a little bit of detail. But it uses binary strings, strings of 0s and 1s. Here, we're going to encode a 4-digit binary string, meaning like a 0110. Which one? Let's just do an example and see how it works. So example, suppose you want to encode what? 1001. This right here is going to be, well, I'll get there. So suppose we want to encode it. How are we going to encode it? Well, what we're going to do is take a Venn diagram with 3 circles. And these 3 circles are going to create 7 regions. And we're going to number these regions. Maybe I should draw this on a larger board. Let's draw it here. That's terrible. So, okay, that'll be good. It might not be larger than my first one. So right here we have 3 Venn diagrams. What we're going to do is label the 3 circles. And the labeling in the order, well, the letters aren't that important, but we have 3 circles. And we're going to number these regions from 1 to 7. And this is important, the exact order. So what we're going to do is 1, 2, 3, 4, like that. So the intersection of A and B is 1, A and C is 2, all 3 is 3, B and C is 4. And then we're going to go 5, 6, 7. That was the oven preheating if those beeps showed up on that microphone or were caught by the microphone. So we're going to take this Venn diagram, and what we're going to do is fill in the Venn diagram 1 through 4 with these numbers. A, B, and C I'll mention in a moment why we're labeling them. So 1, 0, 0, 1, we're going to put them in 1, 2, 3, and 4. And again, the order is important. So 1, 2, 3, 4. 1, 0, 0, 1. And the rule is going to be, well, maybe I'll, so fill in 1 through 4 with the thing you're trying to encode. Next, fill in, now here's the big rule, 5 through, how we fill in 5 through 7 is going to be what matters. Fill in 5 through 7 so that the sum in each circle is even. So fill in the remaining 3 regions so the sum in each circle is even, so that the sum in A, the sum in B, and the sum in C is even. And there will be a third bullet there. So how do we fill these in? Well, let's look at circle A. Circle A is the these 4 regions. Right now the sum is 1. All we can fill in are with 1s and 0s. We're looking at binary strings, and we're going to turn it into another binary string. So we have 1 plus 0 is 1. So what we need to do is put another 1 in there so that the sum in A is even. Well, now we do that for B and C. So B, well, I guess I'll just shade that in more. B, the sum in B right now is 2, which is even. So we'll put a 0 there to preserve its evenness. And in circle C, the sum already in circle C is 0 plus 1, which is 1. So we need another 1. And once we've filled them in, we can use that to encode our binary string if we just write the numbers from position 1 through 7 in order. And the order does matter. So 1, do it in order. 1, 2, 3, 4, 5, 6, 7. So 1, 0, 0, 1, 1, 0, 1. So we want to encode 1, 0, 0, 1. We fill in our Venn diagram with those, well, with these 2 rules, and then this third rule tells us write them in order, and that is how 1, 0, 0, 1 will be encoded. So fill in the Venn diagram. You can see with this Venn diagram it will work for only encoding 4-digit binary strings. Now this, so if you were encoding 1001 and you wanted to send it somewhere and that somewhere knew how you were encoding it, well then it could figure it out. But if it didn't know how you were encoding it, just got this, well it would be an incredible stroke of luck if it guessed that you were doing 1001. Now, right here, the encoding it's doing may not seem all that useful because it does just encode it as the first 4 digits. But there's no reason to assume that that is how, like if you just received, like say you were just walking down the road and a paper with 1001, 101 flew into your hands. You'd be very unlikely to interpret that as just 1001. So it is a useful encoding method. Now, why is it useful beyond the fact that it is encoding? It's writing something as something else. Well, this is what is known as an error-correcting code. And I'll write that as a remark. This is an error-correcting code. What does that mean? Well, it means if the received message for some reason were not 1001, 101, well then you could figure out actually what the message was meant to be. I should have finished this example. Let's say, as a concluding sentence for this first example, instead of just circling that, I'm going to say 1001 is now encoded as. So this would be a more illustrative conclusion to reach in that first example. 1001 is encoded as 1001. Now this is what's known as an error correcting code. So let's look at this example to illustrate what this means. Suppose the received message is received as, instead of that, suppose you got the message 0, 0, 0, 1, 1, 0, 1. And there's going to be another sentence at the end of this example. So leave a space for a sentence. There's going to be something that ends with a question mark. I'm going to go through this and then give away the punchline. So suppose the received message is received as 0001001. Well, first question, is that a valid code given this? Well, you might look at that and say, well, yeah, it's valid. I was supposed to get 0001 because I know that the first four positions are right. Well, not necessarily true. This may not be a correct message. How can we figure out if it's correct? Well, let's fill in a Venn diagram. So again, there's going to be a question here at the end of that example. But I don't want to give away the punchline yet. I'd rather build up to the punchline. 00011001, so write it in the proper order. 0, 0, 0, 1, 1, 0, 1. Is that valid? Well, what rules do we have? The sum in each circle must be even. So, so first we're going to check if this is a valid code. Is this a valid code? Well, if the sum in each circle is even, then it's a valid code. What's the sum in circle A? 1. What's the sum in circle... Well, so right there you know it's not valid. But let's still look at the rest of the sums to figure out even more. What's the sum in circle B? 1. It's very not valid. What's the sum in circle C? 2. Well, this tells us that... Well, now, how should I say it? This information that we found using these circles tells us exactly which one position the error occurred in. So we received this message, and right here we're observing there is a mistake. And this Venn diagram and these observations will tell us exactly where the mistake was made. Where was the mistake made? Well, it was made in A and B. What's A and B? Well, what's in A and B? Where's my blue marker? Usually it's in my pocket. This, I would normally write this over there. So if you have space in your notes and you're taking notes, you can write it next to those arrows. This tells us the error occurred probably has 2 R's. There, now it has 2 R's. Maybe it has only 1. I don't know. This tells us the error occurred in position. Which position? Well, it occurred in A and B. Which thing is in A and B? That piece is in A and B, which, remember, is position 1. So right now I'm going to fill in this question. is this a valid code, and if not, in which position did an error, well, I should say did the error. This detects only one error. I mean, it's not going to detect if there are two errors. So in which position did the error occur? So this tells us, the Venn diagram tells us the error occurred in position 1 because that's where we had odd sums. So this is not a valid code. The error occurred in position 1, and I can actually throw on another question at the end of that. I could say also at the end of this, what message should have been received? What should have been received? Well, we have that error in position 1, so let's just fix position 1. So the error that should have been received is the one that we knew should have been received. But if you didn't know that, then you could have figured it out based on this observation. So right here we have a way to encode 4-digit binary strings. Now practice this example. The order is really what matters. The order of, making sure you're following 1 through 7, and being careful with that. Then you make sure the sum in each circle is even. You can use that to encode, and you can also use that to check if a received code is possible, and if it's valid, and if it's not valid, you can figure out where an error occurred. In this case, an error occurred in position 1. Let's next look at a couple ways we can compress data. So we're going to look at 3 ways we can compress data in an encoding way. The third one's going to be much more complicated than the first 2. But the first one may help us get to the third one. Well, it may help us see how we can, why the third one might be relevant. My erasers aren't working that well. It's getting awfully used. So let's look at data compression now. And let's just give you a rule. Example. A maps to 0, 0. C maps to 0, 1. T maps to 1, 0. G maps to 1, 1. Encode. So we're going to do this example, then we're going to do a second example that looks very similar. So A, C, T, G, these are the... I'm not good at biology. These are the DNA... I think it starts with nucleo. Nucleotides? I don't know biology. They're the things in DNA. I don't know. Maybe I should have looked up the word before doing this. But we're gonna encode AAA, CA, GT, AAC. AAA, CA, GT, AAC. Okay? Well, every A gets replaced with a 0, 0. So we have 3 A's, so we have 3 0, 0s. C is 0, 1. A again, 0, 0. G is 1, 1. T is 1, 0. A is 0, 0. So we have 2 more A's. And C is 0, 1. So just using those rules, we have encoded. Now, that's a lot of numbers in our encoding. So you might make some observations. Now, if we look at that string of letters, A shows up a lot, C shows up a little, G and T show up only once. So suppose you observe if A occurs most frequently, C next most, and G and, I guess I wrote T first, and T and G least, the following gives a more efficient encoding. So the following rule will give a more efficient encoding. And let's use the blue marker for this. The following gives a more efficient encoding. And I will give it to you. A goes to 0. So there we have A taking up 2 characters, but here it'll be just 1. We'll have C going to 1, 0. We'll have T going to 1, 1, 0, and G going to 1, 1, 1. Now how do we encode that? Well, let's encode that again. And I'm actually going to write it, maybe I should have mentioned this. I'm going to write it right under here. Yeah, I will. I'm going to write it right under there in blue because I have blue. If not, you can just write it over there. You'll still see what I want you to see. A gets replaced with 0. C is 1, 0. A is 0. G is 1, 1, 1. T is 1, 1, 0. A is 0. A is 0. C is 1, 0. So with this first method of encoding, it took what? 1, 2, 3. It took 20 numbers to encode that. But with this second one, how many numbers did it take? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It took 16 numbers to encode that. So as we can see, well, 16 is less than 20. So this is, in fact, a more efficient encoding mechanism for this example. So this would be an example of compressing this data into that sequence rather than this one because it does take up less space. Now this right here was based on this remark, a probability remark. A occurs most frequently, C occurs next most, T and G least. So we let A be 1 number, C be 2, T and G be 3. So there is an obvious question. Where did these numbers come from? Why did I choose these numbers? Well, I chose these numbers for 2 reasons. 1, the book used them. But 2, these numbers are useful because not only does it allow us, do each of these sets allow us to encode, they both also allow us to decode. Meaning, if we were given this and this rule, we could get back here. If we were given the blue numbers and that rule, we could get back there. Not any random sequence of 1s and 0s will work like that. So, not the next example, but 2 examples from now, we're going to cover a complicated encoding method, which is a very nice encoding method, but it is based on using the probabilities of the characters in question. So I would like you to keep this in mind before we do the last thing. But before we do that, I do want to do one more example of data compression, because it is a quick example, and I'd rather the last thing we cover in this be the most complicated thing. So right here, we have and as just a concluding sentence, we have a probability observation leading to a more efficient encoding. So that's really the purpose of this one example. The next example is going to, and keep that in mind for the last example we do, actually the last 3 examples we do, they'll all be the same type. Maybe 2, maybe 3, I don't know. But the next type of data compression we're going to look at is called delta compression. I'm going to give you a bunch of numbers. Next, delta compression. Or maybe it's called delta encoding, I should say. But, sorry, the book calls it delta encoding. And it's really the same type of thing. So, but I should call it the same thing the book calls it. Delta encoding. We're going to look at this example. We are going to encode using delta encoding. Encode this string of numbers. This is from the textbook. These are closing prices for a stock in July of 2013. 1615, 1614, 1615, 1632, 1640, 1652, 1653, 1675, 1680, 1683, 1676. So we're going to encode that string using delta encoding. And how are we going to do that? Well, what we're going to do, delta, remember, delta in math, well, it also shows up in chemistry, but delta is used to indicate the change in going from one thing to another thing. So what we're going to do, I'm going to write it in blue. So I'll call it encoding. The encoding for this, and maybe I'll call the other one original. Original and encoding. What we're going to do is take the first number, 1615. And we're just going to look at how that changes, well, how that number changes to the next step. And then we're going to look at how that next number changes to the next step. So 1615 to 1614 goes down 1. So we'll call that a -1. Now we're at 1614. 1614 to 1615 goes up 1, a +1, and we'll just call that a 1. If nothing's written, we'll assume it's a positive. So we went down 1, +1. What about 1615 to 1632? +17. 1632 to 1640, +8. 1640 to 1652, +12. 1652 to 1653, +1. In these, notice we're not comparing this number to the first number. We're comparing it to the previous number. 1653 to 1675, that goes up 22. 1675 to 1680 goes up 5. 1680 to 1683 goes up 3. 1683 to 1676 goes down 7. So we write that as a negative 7. So right here, this string of numbers will encode that. Now, you can see it takes fewer numbers to write this list than it does for this list. Let's say you were typing these numbers on a computer, and you were just writing them in a row. And of course, you wouldn't just write 16, 15, 16, 14. You'd have to write 16, 15, space 16, 14, and so on. So if you just wrote these numbers in the original in a row with spaces between them, it would take, this would take 54 characters to write on a computer, again, including a space between each one. What about over here? How many characters would this take, including a space between each one? A negative counts as a character. Well, putting a space between each one and putting all the numbers gives us 29 characters, again, including spaces. So I'll say including spaces. In both cases, we're including spaces. So you can imagine for huge amounts of numbers. Look at this. This went from 54 characters down to 29 characters. So if you had like a million sets of 4 numbers, and you used this method of encoding in measuring the change between one and the next, well, you'd save up a lot of space. So this is called delta encoding. And there's another example on the worksheet. It follows just like this. So try that one. Oh, no, I should do one other thing with this. Example. Given this delta encoding, go backwards. Given the delta encoding of what? 8, 37, 6, negative 3, negative 15, 4, negative 8, 10, 1, and 7. Given that delta encoding, find, I'll just say find the original. So find what was encoded as that. Well, how do we do that? Well, 837 is going to be the first one. What's the second one? Well, to find this next position, we went 6 up from 837. So we went to 843. Down 3 from 843, 840. Down 15 from 840, 825. Up 4 from 825, 829. Down 8 from 829, 821. Up 10 from 821, 831. Up 1 from 831, 832, and up 7 from 832 is 839. And so that with this delta encoding, we could go in the one direction, we could also go in the other direction. Next, I'd like to take a look at the most complicated encoding we're going to do. It's called Huffman Coding. So here we have an example where we're going to go over Huffman Coding. Now, Huffman was a mathematician in the, I believe, the 50s, the 1950s, and he discovered this method of encoding when he was in grad school. This was one of the projects he worked on in grad school. It's a very important method of encoding. In many ways, it is a best encoding for the types of encoding that we're going to be looking at. In the textbook, in what are we, section 17, we're in chapter 17, this is probably section 3, there is a blurb on Huffman. And I would recommend reading through that. It's like one of those boxed off things at the bottom of the page. Chapter 17, I'm pretty sure it's section 3. So let's look at this example. Given letters with probabilities, use Huffman coding to do these two things. Encode BEECADE and decode this string of binary digits. So we're going to convert these into binary digits using probabilities. So this is similar to the DNA example where we had A, C, T, and G. But in that I gave you the 0, 1 and the 1, 0 and all that. Here we're going to figure out the 1, 0 and the 0, 1s and so on. So we want to encode BEECADE. We want to decode 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 1. And we have letters with probabilities. We have A at 0.09, B with 0.21, C with 0.13, D 0.29, and E 0.28. And of course, and we didn't talk about probability this semester, all these probabilities are going to add up to 1, because one of them will occur 100% of the time, but we're just breaking up the number 1, in this case, into 5 pieces. So let's describe the algorithm. First, arrange by arrange in order of increasing probability. That's a lot of words. So I'll say arrange by increasing probability. So we're going to arrange these in increasing probability. What does that mean? Well, just go lowest to highest, and be very careful each step in this. So A 0.09, that's smallest. Next smallest is C 0.13. Next smallest is B 0.21. That noise was a car driving by. Next smallest is E with 0.28, and then the last is D at 0.29. So first, arrange them in increasing order. Next, step 2 is, I would consider it the hardest step of this. Merge by combining lowest 2 and writing in increasing order. Merge by, and I think that's a little complicated in words, but we'll see what all this means. Merge by combining the lowest 2 and write in increasing order. And we're going to do this until we have just one thing occurring at 100%. Combine the lowest 2. Well, here's how we're going to combine them. AC. AC, we're going to write them like that. The two lowest, AC. The first one we'll put on the left, the second one we'll put on the right. 0.09 plus 0.13. That's a goofy looking 2. See, that's a goofy looking 2. That's a less goofy looking 2. A and C make 22, A or C occurs 22% of the time. So AC 0.22, which is 0.09 plus 0.13. Well, okay. But now we're going to fill it in with the rest of the letters. And we're again writing them in increasing order. So we already took care of A and C. What about B, E, D? Well, we're not going to put B under here because we want these probabilities increasing. So we'll put B up here, 0.21, and then E down here at 0.28, and D next at 0.29. And we're going to keep doing this until we have all 5 written in order. And I'm not going to fit this on the board most likely. So what I'm going to do, you don't have to number these in your note or in your homework or anything like that. But for note purposes, I am going to subcase these. So that was 2A. Next we'll do 2B. This is for board organization. 2B, we're going to do the same thing. Lowest 2. B, A, C. B, A, C. The lowest 2, write the first one on the left, the next 2 on the other side. Yeah, left and right. So I get left and right wrong a lot. This one write first, this one write next. 21 and 22 make 43. And then write the other one. So we already took care of B, A, and C. E and D are now up here. Because again, we want it in increasing order. We want these probabilities always to be in increasing order. Very important. And we're going to keep doing that. So that was 2C, that was 2B, here's 2C. Well, E and D are the top two. So we'll write them like this. E and D, 28 and 29, make 57. And the other one, BAC, we're going to put up here because 43 is less than 57. And then finally, we write them in one string. First one, next one. B, A, C, E, D, and that adds to 1. I mean, it's always good to verify that you did add them to 1. Well, now what are we going to do? Well, that was the end of step 2. Once you've gotten it, in this case it took us 4 steps to do all step 2. Next, I'm just going to get rid of step 1 because we don't need that anymore, and I need board space. Well, next, how did I write this? Did I just say make a tree? I just say make a tree. Let's see what I said. I didn't say anything. So I'm just going to call step 3 make a tree. Now this tree is not the same as the graph tree we talked about when talking about graphs. This is going to be like one of those prime factorization type tree things. But we're going to start at the end here and work our way back. And here is where, am I going to have enough room? Yeah, I should. Here is where we're going to introduce the binary digits, 0 and 1. So we start with BACED, and we're just going to keep working back. So first we're going to work from here to here. BACED splits into these two things. Into BA and CED. And once we do that splitting, we're going to put a 0 and a 1. And we're always, you could do 1, 0. Don't do that. Just make it the first one, a 0, the next one, the one with the lower probability, we're going to put a 0 on. BAC and ED. The lower probability one, we're going to put a 0 on. The higher probability one, we're going to put a 1 on. And then we're going to keep doing that. So how does... I mean, you could do it step by step. I like just filling in the tree like this. You know, well, the first step, you know, you always have to do that first step. The next one, I just like splitting them up, you know, and then looking at 2A, 2B, 2C, 2D. BAC, how does BAC split? Well, BAC is there. BAC splits like this, into B and AC. 0, 1. How does AC split? AC splits, oh, I guess I did erase it. AC split over here. AC split into A and C. 0 and 1. We're always going to put 0 first. A occurred at 0.09. C occurred at 0.13. So we put a 0 there, a 1 there. And ED splits as E and D. It's split up there from going C back to B. And E occurred first, so we'll put a 0 there. We'll put a 1 there. So right now we've formed our tree. And what we can do with this tree is turn 1, 0, 0, 1, or not 1, 0, we can turn A, B, C, D, and E into strings of 0s and 1s. And we just followed a couple rules. Those rules, and I would not say those rules are simple, but you definitely do get used to them when you work with them a few times. So now we have an encoding. So I'll say we now have the encoding. I'm going to write it A, B, C, D, E like in order. You can write it whatever order you want. What's A? Well, what's A? How do we find A? The way we find A is by going top to bottom. Where's A? A is there. Top to bottom, top, down to A. So to get to A, we go 0, 1, 0. To get to B, 0, 0. To get to C, 0, 1, 1. To get to D, 1, 1. To get to E, 1, 0. So right here we have an encoding. So this question, a Huffman coding question, could be phrased, just find the Huffman coding. If it said find the Huffman coding, this would be your answer. It could also be phrased like this: encode, Bcade, encode, and decode that other thing. And in that case, you'd need to encode and decode. So I'll say Bcade is encoded. What's B? 0, 0. What's E? 1, 0. What's E? 1, 0. What's C? 0, 1, 1. What's A? 0, 1, 0. And you run out of room because you don't think things through. So Bcade, B is 0, 0. E is 1, 0. C is 0, 1, 1. A is 0, 1, 0. D is 1, 1. And E is 1, 0. So that's how that's encoded. The other thing, 1, 1, 0, 1, 5 zeros. 1, 0, 1, 1 is decoded as, well, how do we decode? Well, I would say the easiest way would be start at the left and just write letters once you find this code. It's set up so that there aren't going to be redundancies. I mean, now, if you don't start at the left, there would be. For example, right in the middle of Bcade here, right in the middle of Bcade, you have this 0, 0, but that's not a B, because this first 0 goes with the 1 before it. So how would we decode? We would decode going left to right. In Bcade, does 0 exist? No. Does 0, 0 exist? Yes, that would be a B. And you'd keep going. But here, what do we have? Well, 1 digit. Is 1 in our list? No. Take the first 2 digits. Is 1, 1 in our list? Yes, 1, 1 is D. How about next? Is 0 in our list? Nope. Is 0, 1 in our list? No. Is 0, 1, 0 in our list? Yes. A. Next, 0, is that in the list? No. How about 0, 0? Yes. Next. Once one of them is in the list, you're done with that letter. Next, is 0 on the list? No. Is 0, 0 on the list? Yes. B. What's next? Is 1 in the list? No. Is 1, 0 on the list? Yes, it's down there. It's E. And then the last, what do we have? We have 1 here. 1's on the list. 1, 1 is on the list. It's D. So this is decoded as D-A-B-B-E-D. And you could also decode this up here in the same way. B, and then the next one would be 1, 0 is there, so E. 1, 0 is there, so E. 0, 1 is not there, but 0, 1, 1 is there. So C, and the same thing there, and so on. Now this example I believe might be in the textbook. I'm not positive if they use these exact numbers. That last thing over there, I decided to do this example last semester, and in the time between last semester and this semester, before I say that, I chose this decoding to do that decoding last semester because it was, I couldn't find too many 6-letter words in there, and I wanted it to be more than like the word bed. So I thought, well, dab is a word, and then I just made it past tense. Now, I was thinking in terms of art, like, you dab a, I don't know art words. You dab a painting with a paintbrush or something. I learned since last semester that the youngins have a different meaning for that word. But I would just like to be very clear, that is not what I was thinking when I came up with that example. We could do another example. I'm not going to do another example. I think this was illustrative enough. But there will be one or maybe even 2 of these on the worksheet. I haven't written the worksheet yet. So definitely work on the one on the worksheet. But I'm going to give you another, the actual encoding and decoding. I mean, that's, not usually what would be considered difficult here. What's considered difficult here is usually getting to the encoding. So I'm just going to say verify, so exercise. This is an exercise for you to work on. Verify that the digits, what did I say, letters and probabilities, verify that these letters and probabilities A 0.19, B 0.23, C 0.47, and D 0.11. So verify that those have this Huffman coding. So this is an example for you to work on where you know the answer you're trying to get to. Working on the worksheet, you might not, you might make a small mistake in the middle, and you won't be able to encode or decode anything. So just for additional practice, you can verify. So I have the following Huffman coding. So verify that these letters and probabilities have the following. That says Huffman coding. I screwed up writing both words. Verify that they have this Huffman coding. A is 111, B is 10, C is 0, and D is 110. So go through the listing and order argument, and then the putting them together argument, and then the making a tree argument. And see that you get this. This is correct. And you will notice here, C, with most probabilities, does have only one character. With the highest probability, it has only one character. B, with the next, has 2 characters. The others have 3 characters. This one over here didn't have any with 1 character, but that is because the one with the most probability wasn't like way above anything else. But here, C is way above everything else, and that's going to cause it to have this encoding. So work on this one. That's definitely a good one to work on. It helps you get used to this process. And also, of course, try the one on the worksheet, because this will be tested. Odds are it'll also show up on the final exam, because this is a very important result.